Okay, this is a quick tutorial on how to get the Triggerscope MicroManager firmware up and running. This is the firmware that was developed by Nico Sturman at UCSF, and it works in conjunction with the driver that is supplied in MicroManager. So I've got a brand new Triggerscope 4 board loaded up with 615mm firmware, and I've got a nightly build downloaded here of MicroManager on a relatively fresh computer. So this is using the basic demo hardware config. First thing I'm going to do is go to Devices and Hardware Configuration Wizard. I'll go ahead and modify my existing configuration, which you can see is a demonstration setup. Now, the one thing I'll need to know is what is the serial port number used, or COM port number used by the Triggerscope, and that's assigned by Windows, which is right here. So in my computer, this one's pretty basic. There's not much on there. I've just got one device and it's COM7. Now, a real-world instrument used in a lab is going to have a whole bunch of these. The simplest way to figure this out is just to unplug the USB and see which one disappears. Normally, in Windows 10, it does a pretty good job of not moving these numbers around. In older versions of Windows, this was a magical number and it would move as it saw fit. Especially if you plug the same device into different USB ports. That's been tamped down a bit, which is nice, but if you ever see a hardware problem on almost any device that's using serial or COM presentation as an object, first thing to look at is whether or not the COM port number in your control software lines up with the real COM port number in Windows. This is a really common source of frustration. Okay, so we're in the hardware config wizard. I'm going to go down towards the Triggerscope drivers, and you'll see two different drivers. So this is my driver, the Triggerscope native driver, which runs with ARC firmware, works just fine, but Nico's done a great job of enabling a lot of his utilities to operate with the Triggerscope product using his firmware. So we're going to work on this Triggerscope firmware. We'll add this, and here's where the first thing we'll need to do is choose the port. I'll tell it COM7. Second thing we'll need to do is specify the baud rate. And in this case, the Triggerscope front-end microcontroller will support a wide range of baud rates, but we're going to go with 115.2. That's what the system was originally designed to play with. That's what Nico developed on, so we'll make life easy on ourselves and choose 115.2. Everything else here should be default. Okay. The driver opens up and talks to the Triggerscope. Now on the board, you should see now a ready light illuminate. There's an LED which will only illuminate if serial communication by the host computer has been established. And so this way, we can kind of tell that we've got the right serial port, because if we attempted to open this, the hub would not activate, and in addition, the Triggerscope ready light would not be on. Now I can choose what hardware I want to add into MicroManager from the Triggerscope board, and I recommend you keep this as bare bones as possible. Reason being is you can get a lot of control stuff in here when we have to go play with the device property browser. It's best to leave this as minimalistic as possible. For now, I'm going to choose a TTL 1 through 8 bank, and I'll choose maybe 3 different DAC lines. Now, we'll talk about the TTL 1 bank in just a minute. For DAC 1, I'm going to rename this, and I'm going to call this PyFolk or something. I want this to drive, we'll pretend I'm driving a piezo system. Actually, I don't want to do that. I want to choose 405, and we'll call it V for voltage, and maybe we'll call this, let's just call this DAC 1. There we go, 405 nanometers, DAC 1. And on this guy, I'm going to choose 0 to 5 volts. So depending on the product that you have, the Triggerscope supports a wide range of input voltages, including bipolar and unipolar outputs, but we'll choose 0 to 5 volts. Okay, DAC 2, we'll choose, say, 488. Call it D2, and we'll choose 0 to 5 volts. Now for DAC 3, this is where we're going to pretend I'm using a -5 plus 5, so bipolar input piezo motion system for my Z stage. So here I'll call this PyFolk, and I'll choose -5 to 5. Okay. Got my hardware ready. We'll go to the next page. It's also recommended, at least this is my own personal experience with MicroManager, I like to create a fresh configuration and load one device at a time and then play with that device. That really helps to reduce the chaos level when you're adding multiple devices into the system. At the very minimum, you can create a config, play with one device, make sure it works okay, modify that config, and just save it as a new file. These files, it's not like they're taking up a lot of space in your hard drive. So having a couple files where you have maybe your camera first, then you have, the camera and then the stage, and then the camera, the stage, and the Triggerscope, or whatever you're using, but it makes life a lot easier. Okay, we don't really need to set up delay times here. We can choose states if we want to. That reminds me, I want to grab a couple more things, and this is really a big feature of what Nico has set up with the utilities functions in MicroManager. So we have this DAC device, but what's going to happen is when we take a picture, for instance, there's not really a way right now to tell our software that, like, hey, this thing needs to be a shutter or it needs to turn off when the camera's not exposing. So we want to set that up. Now, if we look at the utilities section in MicroManager, we'll find a whole bunch of stuff. And this is just great because this is exactly what we need. If I scroll down here, the first thing I'll choose is this DAZ stage. This basically tells MicroManager, all right, yeah, I've got a DAC line, but I want to assign that DAC line and treat it as though it is a Z motor. So we're going to add this. We'll call this DAZ. Why not? Well, you could leave it the standard device name, but it's nice if you can name it only for your own ability to understand what line goes to what hardware. The high position here will be 150. I'll pretend this is like a 300 micron range Z stage. +5 on the high voltage. Now the low position here will be -150. And we'll choose low voltage of -5. Guess we can put some zeros in there. Why not? All right, that's set up. Now the next thing is the shutters. So let's assume we've got these TTL lines and they're going to go over and turn on and off blanking for lasers. What I want to do is I'll choose a shutter device that will effectively say, hey, whatever setting you're on when you're on, that's fine. But when the camera stops and I need to close the system shutter, I want to link that up so that if you, for instance, have a laser on and I close the shutter, that laser all the lasers should just turn to off. So that's going to be the state device shutter. We'll call this the Triggerscope shutter. All right, now we can keep going. So, yeah, we'll save this. All right, system's up. Now, once I have the software set up with the hardware operational, it would have complained to me if the hardware was not operational. The first thing I'm going to do is probably edit the system startup. Now, a lot of people don't know this about MicroManager, but this startup is executed on load of MicroManager. So anything you put in here into the startup preset will load up when MicroManager boots. So let's edit this group. And what I want to add here, we'll scroll down to those utilities that we were talking about. Now those are normally going to be towards the end, but let's see. All right, so we've got a TG shutter state device. All right. And we've got a DAZ device. We're going to choose both of those to add into the existing system group. Now for the preset, we're going to edit the preset. And we're going to say the DAZ device on system load should be the PiFoc output port. And the Triggerscope shutter state device should be Triggerscope TTL 1 through 8. All right. We'll save that. And if we really wanted to, we could reload the hardware configuration, but we'll just set that guy there. Okay. Just for fun, let's close and reload this and see what happens. Okay. System startup. Now if I select the TG shutter and we go to the device property browser, we should see that the TG shutter is indeed TTL 1 through 8. Okay, so this TTL 1 through 8 thing, let's deal with that now. You'll notice here there's a couple of entries. I have individual TTL lines and I also have this state entry. So what's going on here? So this is kind of like a quick crash course in computer science, but 8 different lasers provide a really nice value because we can encode those into effectively an 8-bit value, which makes life easy in the computer world. Now, underneath that is a bitmask. So if I look at a bitmask, if I enter a value, decimal value of say 255, that presents 8 different bits being on or off. And if they're all on, then I have a maximum value of 0 indexed 255, or 1 indexed, this would be 256, or 2 to the power of 8. Well, we have 8 TTL channels, so if I use this type of a bit mask, I can use a single digital number sent through the serial line to represent the state of up to 8 different TTL devices. So for instance, if I wanted to have, let's clear this out, let's say that I wanted to have channel, let's say channel 2 active. I would have channel 2 would be active and all other channels would be off. So if I set our TTL 1 through 8 state to channel 2, channel 2 would go active. Now that kind of makes sense because you go, yeah, well, channel 2 is channel 2. What about 3? Let's look at 3. So 3 would be bitmask 1 and 1 are positive. And so then if we were to enter 3 here, 1 and 1 would be positive. So that's where things get a little tricky, right? So now we're looking not at the, it's not like a numeric progression of like 1 through 8 equals channel 1, 2, 3, 4. It's that the bit mask represents the digital number, and we really care about the bit mask. So another way to look at this is we can edit the bit mask ourselves. So any computer has this built in a calculator, whether it's a Windows machine or a Mac machine. But if I, for instance, want to turn on channel 8, I could turn on channel 8. And the value is 128. And so then if I come to the decimal equivalent on the 1 through 8 state and type in 128, only channel 8 is on. Okay, so that's kind of how the numeric assignment of what TTL is on is controlled in MicroManager. So that's a little tricky, but it's a really elegant way of handling communication. So I really like it from that perspective. All right. What this gives us is the ability to represent multiple different lines with a single number. So now I can add into, say, my channel setting. We'll add in, let's say, 405 nanometers, and we'll choose volts. I'll choose 488 volts, and then I'll choose TTL 1 through 8 state. Now in this case, I only have the 2 different outputs, but if you had up to 4, it doesn't really matter, right? It could be any of these. So we'll hit OK. And now if we select, say, the DAPI channel, we edit that preset. Let's go ahead and do that again. But I did. Sometimes MicroManager can get fun. There we go. All right. So for the DAPI channel, I don't want any voltage output on the 48, but I do want some voltage output on my 405 line. And then for this 1 through 8 state, I'm going to set it to channel 1 is on, which will be 1. And we can see channel 1 is on there. And that's it. All right, now we'll go to FTSE. And we'll say channel 48 here, And then I can watch if I want through the bit masks. There's channel 2. And we're good. All right, so if I go back to DAPI now, we can see that this switches, this guy switches, and this guy switches. And then we'll switch over to Fitzy. We'll see them all flip. Cool. So obviously I don't have probably I should have had an oscilloscope set up here. So just kind of have to take my word on it. But when I set the shutter up as the TG shutter now, set system to startup, channel group can be channel, and I run 100 millisecond exposure. If I snap an image, what'll happen is the appropriate DAC line, I was just noticing that didn't happen. I realized it's because I didn't select DAPI. Yeah, there we go. So I'm watching on my Triggerscope and I'm seeing the TTL output LED. There's a status illumination LED that will turn on when TTL output is active. I'm watching that LED go active for the duration of the camera exposure time. So what's happening is MicroManager's state device shutter is turning on whatever state device should be enabled when it's allowed to be quote unquote on. So shutter on plus state on equals the state will go active if the shutter's on, and then if the shutter's off or closed, then whatever is on will automatically get cut off. So this is a very elegant way of handling multiple laser lines, multiple TTL lines. This could be LEDs, it could be anything, but the way that this is set up is actually really clean, and it works great in MicroManager as long as you kind of understand the underlying philosophy of how to configure this. I think that the way Nico did this is near perfect. I really can't think of a better way to handle it, actually. And so, but you do kind of just have to have somebody explain how it works, I think, which is really what motivated me to make this video. I've explained this in a number of different cases when helping customers set their systems up. And so it just kind of became, hey, let's do this. Now, the next thing to talk about is this question of blanking and sequence. So this is, again, a really nice implementation on the driver side of how to handle these common problems with our instrumentation. So I have this blank on thing, and let's take a DAC line, because probably the DAC line is just easier to deal with. Let's assume for a minute I didn't even have a shutter. Like, all I've got is these DAC outputs. I want to run these lasers, right? And they're just on all the time, but if I run the DAC down to 0, they're blanked enough, or maybe they actually turn off, who knows? Well, what if I only want to illuminate the sample when I know for a fact that my camera is exposing? So I want 0 software latency on top of my illumination, right? So imagine that the sequence of events which occurs inside of a software application like this is that in software we say, hey, laser, you turn up a little bit. Okay, so the laser turns up to whatever voltage, and then we turn around to the camera and say, hey, camera, go take a picture. Okay, camera takes a picture, comes back. I'm done taking the picture. Cool. Hey, laser, go turn off. Well, there's obviously some latency there. A lot of that latency is baked into how memory is managed in the computer with the camera, bunch of other stuff. Bottom line, if you said, give me a 10 millisecond exposure, you're probably going to get 12, 13, maybe even 20 milliseconds of illumination on your sample. And obviously that is something we would like to avoid. Now we'll talk about this whole idea of blanking. So blanking tells the system, specifically the Triggerscope, I want you to watch 2 conditions. So it's a logical AND operation. If I've told you to turn the laser on, and if you are receiving 5 volts on the trig in SMA connector, then you can have the output actually on. But if one of those 2 conditions goes to a low state, then turn the system off. Okay, so what does that do? Imagine I tell the system, open the shutter or enable the laser to turn on. But then I've got this 8 milliseconds or 5 milliseconds of camera capture delay before my image even starts to acquire. So even though the Triggerscope has been told to turn on, it doesn't actually output a voltage. Now the camera starts to take a picture, and when the camera expose line goes high, so this is a physical cable attached to the back of the camera, that line is routed to the trig, typically trig 1 input on the Triggerscope. Then what will happen is only when that exposed line goes high will you actually get voltage into your laser and subsequently laser power out. So this will constrain the illumination performance on your instrument to only be hitting that sample with light when the camera is actively exposing. So that'll prolong your specimen, keep things a little bit happier, increase the efficiency of the system overall. Now, all that being said, how do you use it? The first option is, do you want to blank on low or high? So you can say, hey, if I get a high input signal, I actually want the system to turn off. If I get a low input signal, I want the system to turn on. I can just completely disable or enable blanking. So like right now, I don't have a camera plugged in. Thus, if I had blanking enabled and I enabled output on the Triggerscope, nothing would happen. It wouldn't actually enable because it's waiting for this camera signal that it's not getting. So that's blanking in a nutshell. Blanking can be used for any individual DAC output, and it can also be used for the TTL 1 through 8 system. So you can set this up so that your quote-unquote shutter won't work unless the camera's actively imaging. Okay. The other stuff we've got, so the sequence, what sequence does is, in this configuration right here, if I were to open up a multi-D acquisition, take a couple Z positions, you can see our Z stage here. We've got our nice little DAZ controlled. We should be able to go down to, actually don't know why my DAZ device is not working right now. Let's go play with that for a second. Maybe because, did I choose it? Yeah, 0, yeah. Well, it works there. Okay. PyFolk. Yeah, that's what we want. Well, maybe that's not working. DAZ. I'll have to play with this later and see what's going on there. PyFolk state volts falling. That should be on, blanking off, blank on low. Actually, come to think of it, I think this is a bug and it was fixed. So maybe I don't have the newest build that I thought I had. That could be the issue. This might actually be a driver problem. So suffice it to say, when I choose these various, add a couple channels here, various settings, what sequence does is it says, all right, I know that the Triggerscope can capture automatically. In other words, it'll switch the channels automatically without having to talk to software at all. It can also do that with a Z device. Now, under the hood, what this means is that when a multi-dimensional acquisition is configured, and when you don't have hardware that would cause this not to work, you can tell the system, hey, load up all these settings, and then only react to them when you receive a input trigger from the camera. Again, this would be on trig 1. Set up the sequence, hit go, and what will happen is the system will receive configuration information from MicroManager on what to do each step along the way. And finally, when you hit the acquire button, the camera will be told, go take however many images. In this case, let's say we did 10 Z planes and 2 channels, so 20 images. So this system will, or I guess it says 22 here, the system will preload the camera up for a stream or sequence size of 22 images, and then the Triggerscope would be loaded up to control devices based on that. And then finally we'd say go, and the Triggerscope gets armed and waits for the input. Camera takes an image, and basically at that point it just flies. So the Triggerscope goes to configuration 1 in its sequence of events, and then the camera takes an image. Sequence 2, camera takes an image, and all of this is automatically done without the computer having to talk to external hardware during the capture. So this is asynchronous device control based on the camera input, and it is the fastest way. It's a hardware method. It's the fastest way to control device motion in a system like this. So the best way to test this is to test it on something like a Z stage on your microscope. You might wonder, like, well, does this work, right? Well, a simple way to set this up is route your lead over to your from your camera to the Triggerscope. There's an LED on the Triggerscope that'll flash if the camera's actually giving out pulses. You can confirm blanking is working first. Then load up a couple of these channels and run a time point of, say, 10 different loops or whatnot, and make sure that it's running very quickly and that you see the channels switching. 30 milliseconds is a great number for this because it's just fast enough for human perception to see it. And so what you should see is things flipping back and forth relatively quickly. Now, if streaming is not on, another good gut check here is you can come down and say, hey, I don't want to have streaming on, right? So we'll turn this off, or the sequence off. Well, now the system should perform much slower. So it should be pretty simple to determine whether or not your system is working actively with sequence mode. And finally, if you have a Z motor and you use sequence and you look at the images, if the Z motor is not moving and reacting, you're not getting a scan in Z of an object, you pretty much know things aren't working correctly. However, if it steps correctly through the object as you would expect it to, you pretty much know that the Z stack is working. So finally, if you really get into a pickle with whether or not things are working, it's never a bad idea to throw either a multimeter on the system and just slow things down to watch what's happening, or even to hook it up to an oscilloscope, which is the most desirable way to prove the performance of the system. So that's just a quick overview on how to dial in MicroManager with Triggerscope. There's obviously a lot of other ways to handle things. This is a relatively simple example, but I think this covers probably the majority of basic needs, right? It's going to be a couple lasers and a Z motor, or a couple LEDs and a Z motor. That's a pretty common setup for the Triggerscope with MicroManager. Any other questions or inquiries related to how to do this, feel free to comment or contact me directly at ARC, and either one of my engineers or I will follow up with you. In addition, the ImageSC forum is a great place to post questions like this.